Surjeet Rajendran, welcome to the show. Hello.
Hi.
I'm going to introduce you in 3 bullet points to our viewers and listeners so that they know a little bit about you.
Sure.
Surjeet Rajendran is a physics professor at Johns Hopkins University, and previously he was a physics professor at Berkeley. Surjeet received his PhD in physics from Stanford and his bachelor's in mathematics from Caltech. Surjeet researches topics in physics beyond the standard model, including dark matter and the quantum nature of gravity. Hello, Surjeet.
Hi, Sanya.
Hi, really glad to have you on. So I'll just add a couple of other things. This specific interview of me interviewing you about this stems from a conversation that you and I had walking around drinking tea or coffee. But when you brought this up to me, I said, what? Are you serious? And it formed the impetus of me wanting to have you on this show.
Oh, that's wonderful. It was certainly a great conversation. So, it's good that you felt inspired by it. Yeah.
And I'll even add, it was at the very beginning of when I thought of creating such a show. So thank you for the impetus. And I'll finally add that the way Surjeet and I met was at a biryani shop.
That is correct. That is correct. Yeah. It was also a great biryani place. So,
Yeah, we met at a place that had great Indian food, and we literally were just sitting next to each other, started talking over a decade ago, and just have kept in touch for years.
That's true. That's true.
Yep. So to start this question of that we explore in this show, could we start with what is your field? What is the field that you are in?
My field is particle physics. So I study basically the fundamental laws of nature that govern how particles interact with each other.
And how is particle physics different from physics?
Well, I would say it's kind of a subfield of physics in some sense. And this can get kind of controversial with some people, but I will say the sort of controversial view of it, which is to say that people who study particle physics believe that they are studying fundamental physics in that, what are the fundamental constituents of nature? So we're always trying to understand the smallest parts of the world. Okay, so historically, this would have been back in the day, someone would have said atoms were fundamental. And then over time, we learned that atoms were made of smaller things called nuclei and the electron. And then we learned that the nuclei were made of things called, protons and neutrons. And then smaller bits like quarks, stuff like that. So basically, a particle physicist tries to break up matter and try to go to the smallest possible thing. And the idea is that if you understand that, you can then try to build up the whole structure on top of it. That is one view. Okay, it's also called reductionism, in that you're trying to reduce everything down to the fundamental constituents.
Thank you. That's really helpful to think about it as, look, how detailed can we narrow this down?
Right.
Within your field of particle physics,
yes.
What do many other physicists believe?
Well, so one of the things that people often believe in my field is that it is impossible to make a universe undergo what is called a bounce. Okay, so a bouncing universe is the idea that the universe was at some point crunching, as it was shrinking, and then it is supposed to re-expand. Okay, so
can you say that in more plain language?
Okay, so we know that our universe right now is expanding. That's something that we have known a long time ago, right?
So that's not disputed. That's not disputed between physicists and lay people. That's just, we all believe that.
Yeah, we know it's true. It's observationally known. So now if you look at that observational fact, it makes you ask the question, well, let me turn the clock back and see how the universe must have been. So if I turn the clock back, you would have found that the universe was smaller and smaller and smaller. Right? Now comes the question, ultimately it gets very, very small. And what happens at that point?
Well, so what I learned when I was a kid is that the Big Bang happened and everything exploded. And from that, everything started expanding.
Right. So that's exactly what people say. They'll say there's something called a Big Bang. And so the sort of the fancy way of saying it is that there was what is called a singularity, a point of infinite density, whatever, from which everything emerged. Okay. Now the question is like, well, what happened prior to the Big Bang, just before the Big Bang?
That's funny. I've
One,
actually never thought about it. You certainly don't study that in school. What happened before the Big Bang?
yeah,
Okay.
so some people would even make the claim that, oh, that is not a well-defined question because we don't have the laws of nature, you know, because when we hit a singularity, what it means is that our current laws don't work anymore. Okay, so the question becomes, okay, it's true, you know, we are, you know, we know so little, and maybe there are some other laws that work at that point. That's a very natural thing in physics. And then what you're asking is basically, well, okay, I hit a point where my theory broke down, right? When I go back in time, what happened before that? One very reasonable possibility would have been that, well, the universe, you know, as we go back in time, shrinks. It hits this point where, you know, our laws of nature break down. But perhaps once you go past that point, maybe the universe was re-expanding. Okay. So like basically the idea would be that if you look back in time, the universe was shrinking, it got to some finite size and then re-expanded.
So are you saying it's possible that rather than all of us having come from the Big Bang, it's almost like from this expanding, we went to the big smallness, and then that might have
It's called
come
the big crunch. Okay, that's the word people use.
the big crunch. So instead of the Big Bang, there may have been the big crunch.
Well, so yeah, so the way the big crunch would work in the usual way it's used is that you don't talk about it from, you know, from here and sort of looking back. You would say, look, if I went to the far past, what would have happened is that that universe was kind of shrinking, and then it was crunching, and then re-expanded. So so that's what's called a bounce. Okay, so you're kind of shrinking, you're crunching, and then you hit a minimum size of some kind, and then you bounce and re-emerge.
So are you saying that a lot of physicists, and certainly I would say most lay people, believe in the Big Bang?
Yes.
And are you saying that your belief is different?
Well, I would say that people, I mean, okay, so it's a question of what one means by the Big Bang. So there is a sense in which I believe in the Big Bang, which is to say that there was a point of, you know, very large energy density or whatever from which we emerged.
Okay.
You can define that to be the Big Bang. Some people think of the Big Bang as a point where before which there was no space-time at all.
Right.
So that is the version that I don't believe in.
And why don't you believe in that?
Because of the fact that I see no particular reason to kind of take that point of view, in the sense that, you know, I would say that as you turn the clock back, what happens is that our theory gets to a point where I don't trust it anymore.
Tell me why. Like, can you expand on that? Why do you not trust the theory anymore? What happens?
It's fundamentally because, you know, as we go back in time, the universe is shrinking, right? Which means that the energy density, the matter in the universe would have all been a lot closer to each other. And as the matter gets closer and closer, the gravitational forces between them get stronger and stronger.
Okay.
And eventually there comes a point where Einstein's theory of gravity breaks down, in the sense that, you know, all physical theories, one should only regard them as approximations of some kind, right? It's like this is actually a fundamental point, if I may spend some time elaborating on this.
Yeah, please.
Okay, so let's ignore the universe and all that stuff and just talk about something very simple like an electron. Now I know that if I have an electron in my hand, that electron has some electric field around it.
Okay.
And that electric field, you know, is 1/r². That's how it drops off. Gauss's law, what you know. And you can now go ahead and calculate the energy density that is in that electric field. And the formula for the electric field, the formula for the energy density is that the energy density goes as the square of the electric field.
Okay.
Now the electric field drops as 1/r², which means the energy density drops as 1/r⁴.
Okay.
And now you can try to ask, well, what is the overall energy density in the entire electron?
How would you determine that?
Well, because you have a formula now, you know that the electric field is 1/r², the energy density is 1/r⁴, and you can do some integral, in the integral of d³ of the energy density, which if you do the integral scales as the integral of dr/r.
Okay.
Now the question is, as you do that integral, you realize that if you do the integral from the point r equal to 0, that is an infinity.
Okay.
Right. So if I do that calculation, all I did was say that, oh, I have this electron, and this electron has some electric field outside. Because of the electric field, the energy density is some quantity, and if I ask the total energy, I have an infinity. So that means that the moment I have an electron in my hand and this electron has electric charges, you think, my God, this electron should be incredibly massive, but it's not, right? So what happens is that basically now I've given you a theory, and that theory is telling you that the electron should have an infinite mass, but it doesn't.
If you take that integral from r equals 0.
Exactly. So what this means is that because electron mass is finite, it means there's something wrong with you taking that integral all the way to r equal to 0.
Okay.
And in the real world, what happens is basically that once the the distance r is less than the so-called Compton wavelength of the electron, like the electron mass somehow, then the classical theory breaks down and is replaced by quantum mechanics.
Okay, so if I expand, can you make that statement more general?
Yeah, so what we would generally say is that if I take any theory in physics, right, you will come to a situation where that theory, you calculate something about it, and sometimes it'll end up predicting infinities.
So for example, a boundary condition or the extreme of that theory.
Yeah, exactly.
Okay.
That's right. Yeah, exactly. So usually it'll be something in the what we would call the short distance or the ultraviolet, which is usually as you go towards r equal to 0, you're going to find that something is blowing up.
Okay. Okay.
Right. And what that means is basically the statement that, well, I've taken the theory to a regime where it's no longer valid.
So what do? Do you dismiss the theory? Do you say it just doesn't work in some situations?
You say it doesn't work in that situation.
Okay.
Because, the theory of the electron's electric field working as 1 over r squared works beautifully to describe how electrons work, in all the macroscopic situations that we use.
Mm-hmm.
But when I try to think about the electron really, really close to it, the classical theory breaks down. And that's why you have quantum mechanics in a sense. Right? So the same thing is true for general relativity, the theory of gravity. So as you go to shorter and shorter distances, very close to a mass or things of that sort, you will find that Einstein's theory also predicts infinities.
Okay.
That means that as you look at the universe and these densities get very, very big, there'll come a point where these densities are so large, the gravitational field is so big that Einstein's theory breaks down. Like there's an infinity in the problem.
Okay. Okay.
And anytime you see an infinity, you say, okay, what that means is that I don't know what the new theory there is. Something else must come in and fix it.
Okay, so bring us back to the Big Bang and the Big Crunch with this.
Exactly. So the idea then is that if you look at our universe today, it's expanding.
Mm-hmm.
You look back in time, it's crunching, it's shrinking. As it's shrinking, the known matter density that's already here today will get closer and closer to each other. So the density gets bigger and bigger and bigger. And as the density gets bigger and bigger, there'll eventually come a point where the density is so large that Einstein's theory, which I was using to predict how the universe is expanding and all that stuff, breaks down.
Okay, all right, very interesting, okay.
Okay. And now the question is so you could define that point to be the Big Bang, which, I have no quarrel with that. That is the Big Bang in the sense that that's a point where the theory broke down and I know I came from it.
Okay.
The question becomes, well, what do people think happened just before that, right? So there's a new theory before that.
And you're saying a lot of people say we don't know. A lot of physicists say we don't know.
Yeah, that is a correct answer. People don't know. Yeah, that's true. There's a very reasonable possibility we don't know. But there is also, I think, a pretty significant belief in the physics community that somehow before that, even space-time did not exist.
I see. Okay. Okay.
So you remember when we say nothing, right? So if you say nothing, for a physicist, nothing is very interesting in that when we think of nothing, is what we call the vacuum, and the vacuum still has space and time in it. It just that there's no particles. Okay, but when these guys are talking about nothing, they're talking about not even space and time existing.
What does that mean? Space and time don't exist.
Well, it's a very weird field. I mean, we don't know what it means. Like there's a strange equation. Okay, it's called the Wheeler-DeWitt equation, and then it predicts various things. And one of the things it can do is produce the universe from nothing, like literally nothing, right? I mean, I don't think it makes a whole lot of sense.
Okay.
Right? So what I would say is that from the physics perspective, if I go back in time, I get to a situation where the densities get very large, general relativity is broken down. And I don't see any reason why we have to give up on the notion of space-time itself at that point. There's a new theory.
I see the distinction.
The space-time has existed forever, right?
Mhm.
And there's just a new phase of matter that we don't quite understand what it's doing. And then we can ask, well, what are the possible behaviors that that phase of matter could have had? One possibility is that you get to this high density and then you just remain that way for a long time, forever.
Okay.
Or you could have gone to that high density and then gone back to low density.
What would cause that? What would have caused from expanding to contracting and then to expanding again?
Right. So if you ask, why are people skeptical of this a bounce, right? What is the reason why people are skeptical of a bounce? The generic reason why people are skeptical of a bounce is basically because they would say, look, let's look at what a bounce requires. Okay. A bounce requires matter to go towards each other as the universe is crunching, and then it has to re-expand.
Mm-hmm.
Now, you might think that as matter is collapsing, right, the gravitational forces between the matter get stronger and stronger and stronger because all the matter is very close. And then the natural thing to think about is that, well, as they get closer, the gravity gets stronger, they're going to keep going, closer and closer to each other. So how are they able to re-expand? How can it bounce out? It has to fight off gravitational attraction. And that is what many people believe is impossible.
Mm-hmm.
And I think is actually very reasonable. Okay. The reason why I think that is actually, I have multiple reasons for this. One reason is just this interesting fact, right? No matter how you slice it, we exist. We can't argue about that. Okay. Now you ask in the standard Big Bang place, how do we exist? Well, you go back in time, you will get to a point where the density is very big.
Mm-hmm.
But somehow or the other, we managed to expand out from that region.
Yes.
So if you think about a bounce, what is the hard part of a bounce? The hard part of a bounce is not matter going towards each other. That's super easy.
Why is that easy? If we believe that the universe is constantly expanding, why before this 0 point, why would it have been contracting?
Oh, I'm just saying it's a possibilities, right? So it's
Okay.
a question of like, if I set it off that way, it is very common in our world that gravity attracts stuff, right? So the fact that I put a bunch of matter and the matter wants to go towards each other is a very normal phenomenon that we see all the time.
Like you mean gravity? Like
gravity, yeah. Yeah, if I drop something, it goes down, right? Things want to go towards each other due to gravity.
But at the same time, we're now in a place where everything is expanding. So
Yes.
both things are true at the same time.
They're both possible behaviors of gravity.
Okay. Okay, keep going.
So, yeah, right. So the thing is, so matter going towards each other is very reasonable, no big deal. And then it gets gravity gets very strong, very reasonable. Okay. The hard part of a bounce always is the re-expansion. Like, how did the matter emerge from this thing?
Okay, and how do you answer that?
And I would say, look, I don't know how it exactly happened, but it happened in the sense that whether I believe in my bounce or something else, it is certainly the case that when we go back in time, we came from a point of very large density and we emerged from it, right? So basically, here's what I'm saying. I'm saying that if you go back in time, there's a point the density was very big, gravity was super strong, but through whatever hook or magic or something like that, we came out.
So you're making a logic-based argument.
Yes.
Because we did come from a contracting place, that must mean that contracting place came from something.
Yeah, exactly. That contracting place came from something. And the hard part of doing that is basically beating gravity and getting out.
Yeah. Yeah.
Right? And clearly that happened. I don't have the equation for it, but clearly that happened.
But how did it happen? How could that have happened? So gravity sucked everything in, everything's together. It's very strong gravitational forces. Everything's a pull. What would make it that bounce that you described?
Well, it would just be a new theory of gravity, for example, right? So in a sense, you're getting to a point of large density, and at that point, the theory of gravity broke down.
And we don't know what's in place of that theory.
You don't know what's in place of it. So I'm just arguing about a phenomenon, right?
Okay.
Is it reasonable that this phenomenon happened? And I would say it is reasonable that the phenomenon happened because we exist. I may not have the equations for it, okay? But, we clearly got out somehow.
Okay, okay.
And this also ties in with another problem in physics and this is funny because like everyone believes this phenomenon, right? Which is the phenomenon of what's called black hole evaporation.
What is black hole evaporation?
So the idea of black hole evaporation is that you take a bunch of stuff and let's say you form a black hole. What we know is that you might think naively a black hole is something from which nothing can ever get out, right? That's the conventional picture of it.
Absolutely, yeah.
I mean, I wouldn't say conventional, it's what the popular science picture of it is. But one of the things that Stephen Hawking showed was that that picture is inconsistent. It's not consistent. That in a world where there's quantum mechanics and this thing and black holes, what happens is that black holes have to evaporate away.
So you're saying instead of everything being sucked into a black hole, that black hole itself, or that also happens? Everything.
Yeah, so you form a black hole and then the black hole evaporates. It produces radiation and then disappears.
Okay, so physicists do believe this.
Everybody believes this.
Okay.
Okay. So now comes the fact, right? So if I look at how this black hole process is happening, it's very much like a bouncing universe. I take a bunch of particles, I put them all together. They're going to go, gravity gets so strong. Hell, they form a black hole. And we don't have the equations to describe the next step very well. But what everyone believes is that that black hole doesn't remain as a black hole. It produces particles and gets out.
Oh, how interesting.
Right? So people don't understand this phenomenon very well. There's no equation for it just yet, but the phenomenon is something that everybody believes. And so I would say that, if you put these two facts together, the fact that we at some point emerged from a point of very high density, and the fact that everyone believes that black holes evaporate, there is extremely good reasons to think that we have, in fact, that we can emerge from strong gravitational forces. And once you can emerge from strong gravitational forces, there is nothing wrong with a bouncing universe because, the hard part is the re-expansion. It is not the crunching part.
Wow. So you're saying, I believe in this bounce that certainly many others in my field don't agree with me on. And
Yes.
Part of the reason, at least two reasons that I believe in the bounce is that had to have come from somewhere.
Yes.
And we all believe in this other area, which is called black holes expanding. Is that what you said?
Black hole evaporation.
Black hole evaporation. We all believe in black hole evaporation, which is so similar in structure to this bounce.
Exactly.
Oh, neat.
Yeah. So I've been kind of like, having fun lately when I go and talk to people about these things. And I kind of, because, I talk about the bounce and the others look like, this guy used to be a serious guy. What's going on?
What happened to Surjeet?
Yeah, what happened to this guy, right? And then I say, okay, but let me ask you these two questions. And what do you think about that? And then they're like, very interesting point. I'm like, okay, it's sort of because what I realized is that, and it's interesting, is basically, we had a paper a few years ago about how a bounce could be achieved. In fact, even a calculable one without even relying on unknown theories. It's a technical paper, and people were a little bit, they don't spend the time understanding it because it's a complicated paper. I mean, it's a fair amount of things that people are not particularly familiar with. So I'm trying to like motivate people into like kind of understanding that more. And the hard part is that if you want to convince people to spend time on something, they have to first fundamentally believe. Even physicists, right? You would think, of course, it shouldn't surprise me anymore. It's not like physicists start with reason and come to conclusions. They start with belief, and then various things happen, and eventually perhaps reason at some point comes in, and then you try to get to a conclusion, right? But the first part you have to do in all of these things, of course, is flipping belief. And I found this to be useful, like in terms of just asking them these two direct questions.
So what are the two questions? Can you summarize the two questions? What are the two
questions? The two questions is basically, what do you think happened at the Big Bang? We got out of there, right? So whatever it is that we got out of means that we were able to beat strong gravity.
Okay.
Okay. So that everybody agrees with. In a sense, we exist. You can't argue about that point. And the next question is basically, you agree that if I take a bunch of stuff, I form a black hole, gravity gets strong, and the black hole evaporates and gets out, you were able to beat strong gravity, and you totally believe this. So why do you think that somehow, if it's the entire universe shrinking and re-expanding, it's somehow not possible?
So Surjeet, what I love about this are two things. One is, when you first told me about this, you're basically telling me, Senya, everything that you learned, this is a little bit like Pluto. Like, hey.
It's a little bit like that. Yeah, it has that feeling to it, okay?
Yeah, even more, no, bigger. This is everything that I've learned and my kids are learning at the Big Bang. What if it were the big bounce? So first of all, but second of all, what's intriguing about the way you've described this with the two questions is something you and I have talked about before, which is influence. How do you influence people's thinking? And you're saying, look, I'm just asking two questions, to both of which people are saying, I do. I agree with that. I do believe that.
Yeah.
Yeah. You know, my dad, who I know you know, he writes books. He sometimes describes this kind of phenomenon as dropping a pebble into water.
Right, exactly. Yeah, you got to get that thought in there, you know.
Yeah.
And it's like interesting to see it in talks where I sort of ask this question, and you can kind of see people like kind of connecting it, and you know they're kind of like, whoa, you know, maybe this guy's totally not lost it just yet. So it's an interesting feeling doing that, I think. Yeah.
Phenomenal. Surjeet, thank you so much for being on the show. And as we leave, I'm going to ask you one question. We are not physicists, most of us who are watching and listening.
Yeah.
What is one thing you would like us to know about physics, even though we're not physicists?
Oh, well, I don't know. I mean, in a sense, like that's kind of a complicated question because I feel like for me, physics is such a wonderful thing. It's such a, you know, so I don't know. I'll tell you. Okay, in my opinion, I do physics because it's a lot of fun, and I think that's maybe what I want to get across is the fact that it's an incredible privilege to be able to sit in a chair and then like think about these totally crazy things, and it's a lot of fun in the sense that people often view physics as though it's a very mathematical or technical field. But in reality, the really interesting stuff in physics is often coming up with like, you know, really simple questions. And then it's always those simple questions that get you to such deep things. And I think that kind of is, I think, one of the most important things is that basically, you know, you can literally just think about something totally dumb and inane, like where did I come from? And that's somehow leading into all kinds of stuff. It's kind of a great feeling.
So it's fun, and it leads you to ask simple questions that you can explore in much more complex ways.
Yes. Yeah.
Thank you so much. Super enjoyed having you on the show. Thank you.
It's been fun. Thank you.